Question number 3. A square loop of sides 12 centimeters is traveling at 3 centimeters per second. It is passing through a narrow zone of magnetic field over here with magnetic field strength of 0.85 Tesla, which is at right angles. Okay. Crosses. Okay, we can think of the arrow. Okay, the arrow head would be a dot coming out of the page, so a cross is the arrow tail going into the page. A, for each loop position A, B, and C during the movement, describe the direction of any induced current. Okay, this is where we go back to year 12 right-hand rules. Okay, so it's got a velocity, okay, which is in direction to the right. Okay, so that's our thumb. Our fingers are pointing into the page. Okay, so that's our magnetic field. Okay, and we're asking, well, what direction is the force? Okay, or the force could also be replaced with I for the induced current. So the current is actually heading up in this direction. Okay, or we could say it's going around the loop in a anti-clockwise direction. Okay, for B, okay, if we look at this section of the wire, okay, again our thumb is pointing to the right, our fingers are into the page, okay, and again we have an induced current here heading up in that direction. But when we come and have a look at this section of wire here, and we do our direction of our thumb, again we'll work out that that's also got an induced current in that direction. Okay, so that's pointing, there's an induced current there, there's an induced current going up there, and so effectively you have no net current. And so you ask, well, what's happening with this section of the wire? Well, nothing's happening in that section of the wire, because unless you're ambidextrous, you can't actually have all of these at 90 degrees, and so there's no induction in these two sections, and so there's zero induced voltage or induced current. Over in this section of the wire, this section is out of the magnetic field, so we only care about here. Okay, again, our thumb is pointing to the right, our fingers are pointing into the page, and we get an induced current heading that direction, so our I is going up, or we have a clockwise direction of current. 3b, calculate the maximum magnetic flux that could go through the loop. Well, that's easy. They're at 90 degrees, so we don't have to use any cosines. It's just magnetic field times area. The magnetic field from up here is 0.85, and the maximum area, well, it's 12 centimeters. Now 12 centimeters isn't SI units, so we have to convert 12 centimeters into meters. So it's 0.12 times 0.12 because it is a square loop. Okay, we can type into our calculator. 0.85 times 0.12 gives an answer of 0.012 Webers is the maximum amount of flux that could go in that loop. 3c, calculate how long it takes for the loop to move in the field. Well, if it's travelling at 3 centimeters a second and it's got to travel 12 centimeters, you can immediately see that the answer is 4. If you wanted to use an equation, you could use velocity as distance over time. We're looking for time, so we rearrange it to be distance divided by velocity. It's got to travel 12 centimeters at a velocity of 3 centimeters per second. That gives us a time of 4 seconds. Okay. For D, calculate the voltage induced in the loop as it moves in the field. Okay. So that again is our same old voltage, or electromotive force, equals negative change in magnetic flux divided by the change in time. Okay. So what is the change in flux? Well, initially when it's not even in the loop, it has no flux, and when it's fully in the loop, it has 0.012 Webers of flux. Okay, so it's going from negative 0 minus, because it initially has none, and we're taking away, well, what does it have at the end? It's got 0.012. The negative just simply comes from the equation, and it does that in 4 seconds. Okay, negatives cancel out, so it's 0.012. Actually, we could just leave the stored answer in the calculator, divided by the 4 seconds it takes, because there's an induced voltage of about 3.1 times 10 to negative 3 volts. Pretty much nothing.